right, so let's see.
Ron before today in class was like, "So you're talking a lot about death today. Are you okay?"
Okay, so today I want to introduce what's called the Dirichlet form of a reversible Markov chain, and we'll see that there's a formula for the spectral gap using this Dirichlet form. So I'm going to let P be the transition matrix of a reversible Markov chain with respect to its stationary distribution pi. So we'll define the Dirichlet form. Associated to this pair P comma pi to be so this is the okay, maybe I'll say it's defined. Sorry, it's defined for functions f and h in R to the x. So we have these two functions defined on our state space. Then their Dirichlet form is this script e of f comma h, and it'll be defined by, it's this inner product with a pi subscript of the identity minus p as a matrix applied to f comma h. And we'll be particularly interested in the case where f and h are the same, and in that case we'll just write it as script e of h, or sorry, script e of f. So script e of f is the Dirichlet form of f with itself. Okay, so then here's a lemma. We have that this Dirichlet form of f with itself can be written as 1/2 the sum over states x and y of f of x minus f of y squared times the stationary distribution pi of x and then p of xy. Okay, so here's the proof. So let's define e tilde of f, and we're going to try to show that this is equal to e of f. So let's define e tilde of f to be this thing here. Okay, well this is, we can just expand the square. Okay, so this here is 1/2 sum over x and y of f of x squared pi of x p of x y, okay, minus the sum over x and y of f of x, f of y, pi of x, p of x, y, and then plus 1/2 sum over x, y of f of y squared, pi of x, p of x, y. Okay, but then maybe I'll just say, okay, since p is reversible, pi of x times p of x, y is the same as pi of y, p of y, x. So I could, actually I'll just change it here. I'll just say this is the same as pi of y, p of y, x by reversibility. And then these two sums are really the same thing. I'm summing over x and y, and here I'm just swapping the roles of x and y. So really I can just write this as half of this sum plus half of this sum is just this sum. So I get sum over x, y of f of x squared pi of x, p of x, y. And then this sum still. Okay, and then okay, this, wait, oh, okay, yeah. So here, I want to say that if I sum over y first, well, I'm just like for fixed x, if I sum over y, the sum of p of x, y over all y is just going to be 1, because that's like the probability of going from x to somewhere, which is 1. So this is the sum over x, y, and x of, or sorry, sum over just x of f of x squared pi of x. And for the other one, hold on. Yeah, so for the other one, I can say that this is, okay, it's the sum over x and x of f of x pi of x, and then the sum over y and x of f of y, p of x, y is the same as pf of x, if you expand what this is. Okay, and then the point is that if we go back to the definition of this inner product with the pi, this is exactly the inner product of f with itself. This is just f comma f sub pi. And this is the inner product of f with pf. Or maybe to make it the same form, okay, it's pf with f, let's say. It's the same thing. And then, okay, then I can just combine this and say this is exactly what we want, which is I minus p f comma f, and that's exactly this e of f comma f, which is also e of f. Okay, so they're the same. Okay, so let's now, okay, so I'm going to write, as I've been doing, this, this math BB1 for the function that just sends everything to 1. So this is like the element of r to the x, defined by 1 of any state is 1. And then note that if we take the expected value of some function with respect to this pi, right, so this is like the sum of f of x, pi of x, that's exactly just the inner product of, right, okay, so this is, yeah, maybe I'll just write it out. This is the sum over x and x of f of x, pi of x, and this is the same as the inner product of f with this Blackboard bold 1. Okay, so now I can say how the spectral gap relates to this Dirichlet form. So here's a lemma. Okay, so let P again be reversible with respect to pi. Then the spectral gap, gamma, which is, again, remember 1 minus the second largest eigenvalue, lambda 2. This satisfies okay, so gamma is equal to the minimum over functions in r to the x, such that the inner product of f with this Blackboard bold 1 is 0. In other words, the expected value is 0. And the 2 norm is 1. Okay, so the minimum over all such functions of this Dirichlet form. So, like, for example, one way of getting an upper bound for the spectral gap would be to just pick some function, f, that satisfies these conditions, compute the Dirichlet form, that's an upper bound for gamma, and then maybe if you choose the f in some nice way, then you can get a reasonable upper bound. And I'll just say this is also equal to the minimum over f in r to the x, inner product with Blackboard bold 1 is 0, and f is non-zero, of the same thing, e of f, but normalized by dividing by the 2 norms squared. Right, so okay, so here I'm just like minimizing over functions with this normalization, but alternatively you could just not have that normalization and then just put the normalization into that part there. Okay. So proof. Okay, so as before, let's pick an orthonormal basis of eigenfunctions. So let fj, j going from 1 to the size of the state space, be an orthonormal basis of eigenfunctions of P with eigenvalues lambda 1, let's say lambda j from j equals 1 to the size of x, where lambda j is the eigenvalue corresponding to fj. Okay, and I guess, okay, we can assume that we've chosen it so that f1 is this black orbital 1, and lambda 1 is then just 1. Okay, so if we have some function satisfying these properties, okay, so if the inner product of f with black orbital 1 is 0, and the 2 norm of f is 1, then, okay, we can write f as the sum of, so it's the sum from j equals 2 to the size of x of some aj fj. Okay, so the point is I'm expanding my function into the basis of this orthonormal basis, and when I look at the coefficient of f1, it's going to be 0 because of this. So I don't have to have the j equals 1 term. And then, because the 2 norm is 1, that's exactly saying that the sum of the squares of these coefficients is 1. Okay, then, if I write this Dirichlet form E of f, okay, this by definition is the inner product of I minus p f comma f, so pi. But then this oh yeah, okay, so if I then plug in this expansion, I'm going to get this sum from j equals 2 to the size of x of aj squared 1 minus lambda j. Right, and so this is okay, why is this is this clear, or am I just missing something? So okay, so the f's are eigenfunctions with eigenvalues lambda j. Oh, okay, so then if I do pf, maybe I should write this out. Okay, so it should be I minus p sum from j equals 2 to the size of x of aj fj with the same sum. And then I guess because oh, okay, yeah, I see. So okay, so let me move this in here and say this is this sum from j equals 2 to the size of x of aj fj minus the sum of aj p fj, and then with this sum. Okay, maybe let me just keep this as one sum. So this is aj fj minus aj p fj, and then this of okay, and then p fj is just lambda j fj because fj is an eigenfunction with eigenvalue lambda j. Okay, so here this is sum from j equals 2 to the size of x of aj 1 minus lambda j fj, and then this is the sum of aj fj, and then because the f's are orthonormal, when we expand this out, like if you just expand this as some big sum, the only terms that matter are when, or the only terms that survive are when like the j's are equal to each other. So this we can write as the sum from j equals 2 to the size of x of the inner product of aj 1 minus lambda j fj with aj fj, and then here because the fj's, again, they're orthonormal, so fj with fj is 1, so now we're just left with aj squared. Yes, this is what we wanted. aj squared 1 minus lambda j. Okay, then the point is that because the aj squareds sum up to 1, this is like some, you can think of this as like you're averaging in some way the 1 minus lambda j's. And so whatever this is going to be greater than or equal to what it would be if all of these were lambda 2's. Because like if you replace all of the 1 minus lambda j's with 1 minus lambda 2, that's going to make every term smaller. So then you just get sum of aj squared, which is 1. So this is at least 1 minus lambda 2, which is the spectral gap. Okay, so that's one direction that this, like for every function, this is going to be greater than or equal to the spectral gap. And then we just want to say that, well, okay, you can actually find a function where it's equality. And to find the function where it's equality, you just use, you just take f to be f2. Like that eigenfunction. Okay, so in this inequality here, equality holds if we take f to be the eigenfunction f2, so that shows that actually this minimum is equal to the spectral gap. And then, okay, so this proves the first equality in the lemma. And then the second one is simple. You just sort of, if you had a function that where the 2 norm is not 1, then you just divide out by the 2 norm squared and it works out. Okay, so I'll just say the second equality is simple. Okay. So we'll keep using this this Dirichlet form, but I also want to go back to looking at this this bottleneck ratio stuff that we talked about at some point. Okay, so let me just recall this notation we had from before. We said q of x, y, so x and y are 2 states. We define this to be pi of x times the probability of going from x to y. And then if we had sets of states A and B, then we said q of AB is just the sum over all states x in A and y in B of q of x, y. And then we defined this phi, this capital Phi of a set S, was defined to be this q of S with its complement divided by the stationary probability of S. And then finally we defined this bottleneck ratio phi star to be the minimum over all sets S with stationary probability at most a half of this phi of S. Okay. So here's the theorem relating this to the spectral gap. So let's say if P is reversible, with respect to pi, then we have these bounds, phi star squared over 2 is less than or equal to the spectral gap is less than or equal to 2 phi star. Okay, so I decided that I only want to prove the upper bound here just because I didn't want to do the lower bound. But I'll give a couple of examples first showing that these are essentially both tight, and then I'll prove this. Okay, so, and by both tight I mean like there's an example where gamma can be like asymptotically close to the lower bound, or an example where it's the upper bound. Okay, so one example was, okay, just the lazy random walk on a hypercube. Okay, so for this, let's consider this set S, which will be the set of all states that start with a 0. Okay, then we can compute this phi of S. Okay, so to compute phi of S, we just take this Q of S with its complement. So S is the set of states that start with 0, and its complement is the set of states that start with 1. And yeah, so I want to take this sum, which should be, so it's like the sum over, well, I'll just say x in S and y not in S of Q of xy. So that's this, and then I divide by pi of S. Well, pi of S is just a half, so I'll get a factor of 2 here. Right, the stationary distribution is uniform, and half of the states are in this set. Okay, so we get a 2, and then, okay, well, what is Q of xy? This is just going to be the stationary probability of x, which is, okay, so again, pi is uniform, and there are 2 to the n states. So pi of x for any x is just going to be 2 to the minus n. Right, so we have a sum over x in S and y not in S of 2 to the minus n, and then p of xy. And okay, so this, I can say, okay, I have a 2 to the minus n, and then if I, okay, so p of x, so I want to sum p of xy, which is going to be, what did I write it this way? Well, okay, it should just be the size of S, so that's like the number of choices for x, and then for each x, the probability of going to y is, well, it's 0 if you can't go, like, okay, so because x starts with a 0, and any y in here starts with a 1, the only way you transition is if x and y are equal, except in the first coordinate, and then like this random move, like the probability of going from x to y would then be 1 over 2n, because you have to choose the first coordinate, which happens with probability 1 over n, and then when you do like the random flipping of the bit, you have to choose to change it from a 0 to a 1, which happens with probability 1/2. So the probability of going from x to y is, well, okay, maybe, yeah, it's like there's one y that works for each x, so I'm summing over x, and then for the one y that works with it, which is like the y that agrees with x past the first coordinate and disagrees in the first coordinate, for that one y, p of xy is 1 over 2n. Okay, and then the point is, well, this is 2 to the negative n minus 1. This is 2 to the n minus 1, so this all cancels, and this is just 1 over 2n. Okay, so therefore, because this phi of s is 1 over 2n, that means that phi star is at most 1 over 2n. Okay, but we've seen before, that the spectral gap gamma is exactly 1 over n. So the upper bound here is tight, because this is saying that 1 over n is less than or equal to phi star, which is less than or equal to 1 over n. So actually in this case, phi star, okay, so maybe I'll say the upper bound says gamma is less than or equal to 2 phi star, but 2 phi star is less than or equal to 1 over n, and this is also 1 over n. So in fact, everything here is equal, so the upper bound is tight in this example. Okay, now for the lower bound, let me do a different example. So we'll look at the lazy random walk on a 2n cycle, on the 2n cycle. So we saw that the second largest eigenvalue well, okay, so for the non-lazy chain, we did the non-lazy simple random walk on the 2n cycle. We saw that the second largest eigenvalue is cosine of pi over n. So for the lazy chain, the second largest eigenvalue, lambda 2, is cosine pi over n plus 1 over 2. And then this is 1 minus, well, okay. 1 minus pi squared over 4n squared plus O of n to the minus 4. Okay, but then, yeah, so therefore, if we look at the spectral gap, gamma is pi squared over 4n squared plus O of n to the minus 4. Okay, but now let's look at this Q stuff, the bottleneck ratio stuff. Okay, so for any set S in our state space, which is the 2n cycle, if we look at this phi of S, okay, this is equal to the size of the boundary. Okay, so remember, this boundary of S was like the number of edges going between S and the complement of S. So if you imagine S is some subset of the vertices of a 2n cycle, it's just the number of edges connecting something in the set to something not in the set. And then, okay, let me write out what this is and we'll see why this is true. So we have 1/4, 1 over 2n, and then the size of S over 2n. Okay, this is because I want to take the sum, where's my sum? Yeah, I want to take the sum over something in S and something not in S. So I get, for each edge, I get a term. The 1/4 is coming from, okay, so what is Q of xy if x is in the set and y is adjacent to it but not in the set? Then Q of xy is going to be pi of x, p of xy. The p of xy is the 1/4 because, like, if I'm at a vertex in the cycle, then there's like a 1/2 chance of staying still because it's lazy, and then there's a 1/4 chance of going clockwise, and there's a 1/4 chance of going counterclockwise. So the probability of going from that vertex to the one adjacent to it that you want to go to is this 1/4. And then the 1 over 2n is this this pi of x, just because it's a 2n cycle, and so it's a uniform distribution. Okay, so this is the numerator, the Q of S comma complement of S, and then pi of S is just, well, it's the size of S divided by 2n, because again, it's the uniform distribution. And then this we can simplify as the size of the boundary divided by 4 size of S, right, by canceling the 1 over 2n. Okay, so I'll just say where, remember that the boundary of S is the set of x comma y, such that x is in S and y is in the complement of S.
You accidentally wrote the boundary on the...
Oh, yes, thank you. Yep, good point. Okay, now, phi of S, okay, is minimized. Okay, well, I want to minimize phi of S subject to the condition that that the probability of S is less than or equal to 1/2. And this is when n consists, or when S consists of n consecutive vertices. Right, like that's the way, if you have, your in cycle and you choose just a bunch of, like half of the cycle, then you're minimizing the boundary because now the boundary only has 2 elements, which is the smallest that it could be, and you're maximizing the size of S subject to this condition, so the whole thing is definitely minimized. So that tells us what phi star is. It's going to be this, where this is 2 over 4 times n, so that's 1 over 2n. Okay, so then if we look at the lower bound in the theorem, okay, so the lower bound in the theorem states that gamma is greater than or equal to 1/2 p star squared. Right, and then, yeah, so that's, where did I have this? Here. And in this case, the 1/2 phi star squared is 1/2 of 1 over 4n squared, so that's 1 over 8n squared, which is the correct order of magnitude. So it's not exactly equal, but the gamma here was also on the order of, where was the gamma? Oh, where did I do this? Right. Oh, here, yeah. It's pi squared over 4n squared plus something smaller. And okay, here it's like 1 over 8n squared. So they're both like on the order of 1 over n squared. Okay, so I'm just going to prove this inequality. So let's do that. Okay, so let's say we have some function f with expected value 0 with respect to pi. Okay, then what we can do is write the following. So 2 times the 2 norm of f squared. I can write this as, well, okay, I'll write it as the sum over x in x of f of x squared pi of x. That's just the 2 norms squared, and then I'll just add it again, but with a y instead. Okay, and then this I could write as, so let me write this as the sum over x and y in x of f of x squared pi of x p of x y. So the point is now I'm adding a sum over y in x of p of x y, but that's 1, so I haven't changed anything. And similarly here, I can add a sum over x of p of y x. And then I can write this as the sum over x and y of, oh wait, sorry. Maybe that's not what I want to do. Let me not do this as, okay, sorry. Let me do this as pi of y. Okay, that's still fine. I'm summing over y and x of pi of y. That's 1 because it's a probability distribution. And here I want pi of x. Sorry. And now, okay, now if I take this sum, I'll have the pi of x pi of y. And then I'll have f of x squared plus f of y squared. But I want to write that as f of x squared plus f of y squared minus 2 f of x f of y. And so the point is this extra term gives me 0 because what is this? Like if I just take the sum over x and y of pi of x, pi of y, 2 f of x, f of y, I could split that into a product of two sums. It's the sum over x of pi of x, f of x, okay, times 2, and then like the sum over y of pi of y, f of y, but those are both 0 because of this. So like, yeah, this ends up being 0. And then this I can write as the sum over x and y of pi of x, pi of y, f of x minus f of y, or minus f of y squared. Okay, so by the lemma, some lemma we had, gamma is equal to, so do I still have the lemma written? Maybe I do. Maybe I erased it. Yeah, okay, I think I erased it. So by the lemma, gamma is equal to the minimum over functions f that are not identically 0 of, well, and also that we wanted this e pi of f to be 0, or to be, 0, of this, this Dirichlet form, which is the sum over x, y in x of pi of x, p of x, y, f of x minus f of y squared. Right, so this was, well, okay, I guess we had a 1/2 up front, and then divided by I want to divide by the 2 norm squared, and the 2 norm squared is this thing divided by 2, so I have a 1/2 of the sum over x and y in x of pi of x, pi of y, f of x minus f of y squared. Let me just cancel the 1/2 because that doesn't matter. So then, okay, so we have this for the spectral gap, but now, okay, let me relate this to the bottleneck stuff. So for every subset S of the state space with stationary probability at most 1/2, define a function f sub s on the state space by, okay, I'm just going to let f sub s of x be negative pi of the complement of s for x in S, and it'll be pi of s for x not in S. Okay, so this function takes two values, right? Like these are just, for a fixed s, these are just constants. And it takes this value when x is an s, and it takes this value when x is not an s. And what you can note is that, so note that the expected value of this function, e pi of f sub s, is 0, right? Because if you, well, maybe I can just write it out. This is going to be the sum over x in s of pi of x f sub s of x plus the sum over x not in s of pi of x f sub x s of x, but then this is the sum over x in s of, okay, this is now just negative pi of the complement, and I get, so I have negative pi of the complement, which is a constant, but I'm summing that over every state in s, so I get a contribution of the stationary probability of s. Right, like it's this. This is the value of f sub s of x here, and then pi of s, this sum. And then similarly, here I have pi of the complement, and then each term is just pi of s, and this is 0. Okay, so if I have two states x, y in the set S, then, well, okay, if I look at this f of x minus f of y squared, I get 0, just because, right, f takes the same, or sorry, this should be f sub s, right, because it takes the same values on elements of s. Similarly, if x and s, or sorry, if x and y are both in the complement, then f of x, f sub s of x minus f sub s of y squared is 0. But then, if one of them is in s and one of them is not, if x is in s and y is not in s, then if I look at this, so I should get pi of s, sorry, so this should be pi of s minus negative pi of the complement of s, which is just 1, right? Because I'm taking like the probability of s plus the probability of the complement of s, so that's just 1, and then squared is 1. So if I then go back to this formula for gamma, gamma is, okay, it's the minimum of this. So if I just use the specific f sub s, that'll give me an upper bound. So gamma is less than or equal to sum over x in s, y not in s, of pi of x, p of x, y, plus sum over x not in s, y in s, of pi of x, p of x, y, right? That's just this sum, because I get 0 if x and y are both in s, or if they're both not in s. So I only care about when x is in s and y is not, or when x is not in s and y is in s. And then I need to divide by this thing, and again here, I only have to care about the terms where x is in s and y is not, or vice versa. So I get a sum over x in s, y not in s, of pi of x, pi of y, plus the sum over x not in s, y in s, of pi of x, pi of y. Okay, and then what is this? Well, okay, so this sum is exactly my q of s comma the complement, right? It's exactly this sum that I want. And then this is also the same thing. So this is just 2 q of s with the complement of s. And then here I get 2, and this should be, okay, so if I just write this sum as, I write it as a product of two sums, it's the sum over x and s of pi of x times the sum over y not in s of pi of y, so that's pi of s times pi of the complement of s, and then this is also the same thing. And then, okay, what do I want to do? I want to say that pi of the complement of s is at least a half, because we're assuming that pi of s is at most a half. So if I replace this with a half, the denominator will get smaller, so the whole thing gets bigger. So I get an upper bound if I do 2q of s with the complement over 2 pi of s times a half. Okay, but then the 2 and the 1/2 cancel. And now this is just 2 phi of s. So gamma is less than or equal to 2 phi of s, and that's true for every s with stationary probability at most a half. So it's also, thus gamma is less than or equal to 2 phi star. Okay. Okay, so yeah, I don't have too much time left today, but maybe I'll just start with what I want to do next, which is comparison of Markov chains. So oftentimes if you have some Markov chain, you can try to cook up a related Markov chain that is maybe easier to analyze, and if you can compare them, then you can say, get a bound for the spectral gap of one of them in terms of the other one. Maybe it's easier to compute the spectral gap of the other one. So I'll start by giving an example of this, and then we'll talk more about these comparisons next time. we're going to look at comparison of Markov chains. So suppose, okay, this is the first example of this. Let's suppose we have a subset A of our state space. Then we can define what's called the induced Markov chain, or the induced chain. So the induced chain on this state space A. Okay, so this is the Markov chain with state space A, and it has a transition matrix which I'll call PA, piece of A, and this is given by piece of A of xy. So here x and y are two states in the space A, and this is the probability if I start the original Markov chain at x, that what I'll call x sub tau A plus, and I'll explain this, equals y. So I think maybe we define this at some point. The notation here is that tau A, if I had tau A without the plus, that's the hitting time of the state of the set A, which is the first time that you reach something in A. And if I put the plus, I'm just going to say, okay, it's the first positive time that you reach something in A. So the way you can think of this is, if I start my original Markov chain at x, and then I just run it until I get to something in A, or the first positive time that I get to something in A, then I want to know what is the probability that that's equal to y. So essentially what this is doing is it's sort of like, imagine you have your big Markov chain and then you have your subset A. You're basically only keeping track of the times when you reach states in A. So actually, if you think of the Markov chain, maybe an easier way to think about it is like a sequence of random variables, right? Like when I originally defined a stochastic process, I said it's like the sequence x of t for t at least 0, so you have x0, x1, x2. So imagine you take that sequence, that Markov chain, and you just delete all of the things that are not in A. Okay, well then that's some Markov chain with state space A, and that's induced. Okay. Maybe I'll just write down, okay, where tau A plus is the first positive time, when the original Markov chain reaches A. Okay, so again, the point is we run the original Markov chain and we delete the states that are not in A. So let's see, I have a few minutes, so maybe I can state a theorem and then I'll prove it next time. Okay, theorem. So let's let xt t at least 0 be a reversible Markov chain on state space X with stationary distribution pi like usual. And spectral gap gamma. And we're going to let A be a non-empty set of states, and let gamma sub A be the spectral gap of the induced chain. Okay, then gamma is less than or equal to gamma sub A. So if you take this induced chain, then the spectral gap can only go up. Okay, and I'll prove this next time.